Hello, and welcome to the presentation for Capstone Group SAE Supermileage 2021 Progress Update. Today's presentation will be presented by Scott Miedema, Michael Bertodi, and myself, Cameron McCaig. The scope of this project consists of the following characteristics. The ultimate goal is to design a hyper-fuel efficient vehicle. This will be achieved by designing an exceptionally lightweight aerodynamic body and extremely efficient drivetrain with minimal mechanical resistance. With the COVID-19 pandemic, it is important to note that the team's work will be exclusively theoretical and design-based, thus no manufacturing or physical work will be executed. Therefore, the design will be aimed to compete at the 2022 Michigan SAE Supermileage competition as past years. This means that all of the team's resulting work must have a high emphasis on detailed research and design analysis. To maximize efficiency within the team, subgroups were created. The team was split up into the following categories: aerodynamics and body, powertrain and brakes, and chassis and steering. The group members involved in each subgroup are listed as above. The team's constraints are focused primarily on the SAE Supermileage rulebook to ensure that the vehicle would be eligible for a physical competition in upcoming years. Given the COVID-19 pandemic, the most recent iteration of the rulebook was issued in 2020. Therefore, all regulations will be made in reference to that iteration. The regulations that constrain the design of the powertrain subsystem are the contents of Article 2, 3, 4, and 7. Article 2 describes the power unit itself, where a spec engine is selected by SAE. Further description of allowed and banned engine modifications are listed there as well. Article 3 describes the spec fuel bottle provided by SAE upon arrival at the competition as shown in Figure 3 of the regulations. Article 4 explains the limitations on fuel systems. This section is not part of the scope of this project, but it must be acknowledged during the design process. Article 7 describes the braking system and the safety test the car must pass. The vehicle must be capable of braking from 24 kilometers an hour to rest within a 4-meter distance in a relatively straight line, as shown in Figure 5 of the regulations. These 4 articles are the primary constraints of the powertrain team during the design process. The chassis subsystem is predominantly constrained by Articles 1, 5, and 6. Article 1 ensures that the steering system is capable of achieving a maximum of a 15.2 meter turning radius. It also demands that the structure of the vehicle is capable of holding a minimum of a 130-pound driver. Article 5 ensures that the driver must have access to a kill switch system to remove all live electrical power from the vehicle for safety precautions. Finally, Article 6 demands a roll hoop position 5 centimeters above the driver's helmet, which is wider than the driver's shoulders, and it must withstand 114 kilograms applied from any direction. The body and aerodynamic subsystem of the vehicle is constrained by Articles 1, 6, and 9. Article 1 demands a 180-degree frontal field of view from the driver's position. Article 6 demands the body must include sufficient space for a roll hoop and firewall, and the driver must be able to egress the vehicle within 15 seconds. Finally, Article 9 demands the implementation of mirrors for rearward visibility.
Due to COVID restrictions, many research and development aspects of the powertrain have been limited, shifting focus to the design aspects. The drivetrain will have a single-wheel, chain-driven design adhering to Article 2 in the SAE rulebook. Engine packaging will be optimized within the limited space to give aerodynamics more freedom in their design. Additionally, a hydraulic brake system and clutch assembly will be included with dynamic systems, failure prevention conditions, and computer-aided software models. The chassis will be a monocoque design, with drivetrain, steering components, and driver carefully positioned to balance weight on all 3 tires. Manual steering will be used to reduce weight, as assisted steering is not needed for such a lightweight application. Safety measures will be put into place to ensure there is no restrictions when the driver is in a full steer situation, and also to make sure that the driver's vision is not impaired. Lastly, detailed calculations of vibrations and dynamic components will be assessed. For the aerodynamic team, reducing weight and minimizing drag coefficient will be the most important factor when choosing a final body shape. With the monocoque body, structural aspects will also have to be taken into account as there is no complete frame under the body. Throughout the design phase, dimensions will be checked to ensure that standards are met and that all internal components will have ample room. An important part of the powertrain design is the engine packing. An engine mount will be used to fix the engine block to the monocoque body. Calculations will be made for transmission gear ratio from the driven to the drive gear, as well as fuel efficiency and speed estimates. Right now we're looking at an approximate 16:1 drive to driven gear ratio. This will depend on the wheel size that we decide to use at a later date. We're also looking at different options for clutches to purchase them. And it will be important to get an overall size for the packaging as the engine is one of our biggest assemblies and fitment constraints. Additional to the engine packing, powertrain design will also focus on the braking system. The braking system will be floor mounted to avoid driver sight issues as it is very compact in the body of the vehicle. The master cylinder will be sourced with custom pedals and mounts. A caliper-on rotor design will be used compared to a caliper-on rim setup as it has more braking force. The design setup is still subject to change and modification depending on constraints by other teams.